Carboxylic acid derivatives will undergo a variety of reactions. We're going to begin our focus on nucleophilic acyl substitution reactions, which are very important for the interconversion of various carboxylic acid derivatives. In this video, we're going to focus on an overview of these reactions. Let's consider the reactions of aldehydes and ketones compared to the reactions of carboxylic acid derivatives. In separate chapters, we've talked about reactions of nucleophiles with aldehydes and ketones. And when the nucleophile adds to the carbonyl carbon, these electrons can get pushed up onto the oxygen, giving an intermediate that looks like this. After that, it's possible for this intermediate to grab a proton from water, for example, to give a product that looks like this. Or it's possible that the reaction can reverse, where these electrons can come back in to reform the carbonyl, kicking the nucleophile back out again. As we consider the different types of nucleophiles we've seen, some nucleophiles such as Grignard reagents or organolithium species or hydride reagents, these are going to be irreversible nucleophilic addition. And so once the nucleophile adds, it won't get kicked out again, and the only option is that a proton is grabbed and we end up with this type of product. If our nucleophiles are things like cyanide or an alcohol or an amine, these are reversible reactions that will reach equilibrium. So whether our equilibrium lies toward the addition product or the original aldehyde or ketone depends upon the particular reaction conditions. But one thing that's very important to notice is that whether our reaction goes in this direction or that direction, we don't have another direction where the R groups are kicked out. Let's compare that to the reaction of various carboxylic acid derivatives. Keep in mind that one of the features of carboxylic acid derivatives is that they have a Y group that is capable of stabilizing a negative charge. So when a nucleophile adds, it can also add to the carbonyl carbon, pushing these electrons up onto the oxygen, giving an intermediate that looks like this. Now, there will be a number of differences regarding proton transfer and exactly what the charges are on this intermediate. But the next stage that could happen is that a pair of these electrons on the oxygen can come back in to reform the carbonyl, kicking out the Y group as a leaving group, which would give a new carboxylic acid derivative with the Y group kicked out as a leaving group. So with aldehydes and ketones, these will undergo nucleophilic addition reactions, whereas carboxylic acid derivatives will undergo nucleophilic acyl substitution, where the Y group is replaced by the nucleophilic group. As we consider the interconversion of carboxylic acid derivatives by nucleophilic acyl substitution, we can, for example, have a carboxylic acid derivative react with water to give a carboxylic acid. It could react with an alcohol to give an ester, or it could react with ammonia or an amine to give an amide. These are some of the most common or most useful nucleophilic acyl substitution reactions, but we are going to take a look more systematically at a broader range of nucleophilic acyl substitution. As we're thinking about nucleophilic acyl substitution reactions of carboxylic acid derivatives, we can think about the derivatives as having one of these two forms. We can think about the carbonyl being connected to a group that pulls away electron density from the carbonyl, or a group that can release some electron density to the carbonyl. What impact would this have? If this group is pulling away electron density, then that is going to leave an even bigger partial plus on the carbonyl carbon, which would make it more electrophilic and more susceptible to nucleophilic attack. If we had a group that could release some electron density, then that is going to leave this carbon, we can think of it as having a smaller partial plus charge, and so it would be less electrophilic and less susceptible to nucleophilic attack. Now, as we're thinking about carboxylic acid derivatives, we have our carbonyl connected to an oxygen or to a nitrogen or to a halogen. And all of these are more electronegative than carbon. So if we're thinking about inductive effect, we're always thinking of this situation. However, we have to keep in mind both inductive effect and resonance effect, which can release some electron density back to the carbonyl. As we consider the relative electrophilicity of the different carbonyl carbons, let's consider differences in electronegativity. So let's go all the way back and think about Falkland Birch, where fluorine's more electronegative than oxygen, is more electronegative than chlorine, than nitrogen, than bromine, than carbon and hydrogen. If we're looking at oxygen compared to carbon, there's a bigger difference than between chlorine and carbon or between nitrogen and carbon. So thinking about inductive effect, we would think about this is having a very big dipole, whereas here we have a smaller dipole, and here we would have an even smaller dipole. Based on inductive effect, we might expect esters to be the most reactive because pulling away electron density would leave this carbon with the biggest partial plus, making it most electrophilic. However, in addition to inductive effect, we must also consider resonance effect. Because oxygen and carbon are similar size, we know that they can have very effective orbital overlap, which leads to very effective resonance. And so the oxygen can be electron releasing by resonance effect. Nitrogen is also pretty good at releasing electron density. Chlorine is not quite as good at releasing electron density by resonance. So when we think about the relative stability of the different carboxylic acid derivatives, we need to think about both inductive effect and resonance effect. And the result is that acid chlorides are the least stable, followed by esters, followed by amides. So because chlorine pulls away electron density strongly but doesn't release it back very well, that means that this carbon is the least stabilized, and this will have a very big partial plus, making this very electrophilic. Nitrogen pulls away electron density not quite as strongly, and it can release electron density pretty effectively by resonance. So the net result is that this is not extremely electron withdrawing. So this carbon has a smaller partial plus, is less electrophilic, and less susceptible to nucleophilic attack. In other words, when we think about the relative stability, and now we think about the relative reactivity of these carboxylic acid derivatives, acid chlorides will be the most reactive, followed by esters, followed by amides. Now, as we were trying to compare chlorine to oxygen to nitrogen, we got a few of our carboxylic acid derivatives, but we should also consider where anhydrides fall in this range. So let's compare an ester with an anhydride. In both cases, we have oxygen pulling away electron density from the carbonyl carbon, and in both cases, we have oxygen releasing electron density to the carbonyl carbon by resonance. But if you look at the case of the anhydride, we can think of it as the electron releasing is kind of more spread out because this oxygen has to share in both directions, which won't be as effective as this oxygen sharing in only one direction. So that means that overall, this group is going to be more electron withdrawing than this group is. So when we put this all together, we have our acid chlorides are the most reactive, followed by anhydrides, followed by esters, followed by amides. So this carbonyl carbon is the least stabilized, so it's the most electrophilic and it's the most reactive in nucleophilic acyl substitution. As we move down here, we see that this carbon is going to be the most stabilized, so it is the least electrophilic and the least reactive in nucleophilic acyl substitution. And finally, as we consider nucleophilic acyl substitution as a way to interconvert between the different carboxylic acid derivatives, we need to keep in mind that interconversion works in this direction. So because acid chlorides are the most reactive, they can be converted to an ester, for example. But an ester cannot be converted to an acid chloride by nucleophilic acyl substitution. With anhydrides, because this is a pretty unstable carbonyl, these can be converted to an amide that has a more stable carbonyl. So interconversion works to the right, not to the left. And here's another way to think about interconversion of carboxylic acid derivatives by nucleophilic acyl substitution. Because acid chlorides have the most unstable carbonyl, that makes this the most electrophilic, the most reactive. Therefore, acid chlorides can be converted to anhydrides, they can be converted to esters, they can be converted to amides, and they can be converted to carboxylic acids. Anhydrides cannot be converted to acid chlorides, but they can be converted to esters or amides or carboxylic acids. Esters cannot be converted to anhydrides or acid chlorides. They can be converted to amides or to carboxylic acids, and amides can be converted to carboxylic acids, not to esters or anhydrides or acid chlorides. And don't forget that carboxylic acids can be converted to acid chlorides by reaction with thionyl chloride or oxalyl chloride, for example, or it can be converted to an acid bromide by reaction with phosphorus tribromide. For the last bit of our overview of nucleophilic acyl substitution, before we get into the details of the specific reactions, I want to think about the overall mechanism, which happens in two stages. So first of all, we have the formation of a tetrahedral intermediate, followed by the dissociation of a tetrahedral intermediate. So if we're starting out with this generic carboxylic acid derivative, it can react with a generic nucleophile, where this nucleophile will share its electrons with the carbonyl carbon, pushing these electrons up here, which would give us an intermediate that looks something like this. Now, this is not necessarily going to exist, especially if our nucleophile is oxygen, then we can't have an O plus and an O minus in the same molecule. This could be in different protonation states. This could be already protonated so that when the nucleophile adds, this would have a positive charge and this would be neutral. Or instead of being protonated, this could have a negative charge so that after it adds, this might be neutral and this would be negative, for example. But proton transfer to and from oxygens would be rapid to give a tetrahedral intermediate that looks like this. Notice we have changed from having an sp2 hybridized carbon to an sp3 hybridized carbon, which is now tetrahedral. So this is often referred to as our tetrahedral intermediate. Next, as we consider the dissociation of the tetrahedral intermediate, again, this can happen with differences in terms of proton transfer. If we have something acting as a base, this doesn't mean we have to add sodium hydroxide. It could just be the solvent that is acting as a base or acting as an acid as needed. But let's say, for example, our solvent acts as a base. It could grab off this proton, allow these electrons to fold in here, kicking out the Y group as a leaving group, giving us our new carboxylic acid derivative and Y minus as the leaving group. So formation of the tetrahedral intermediate, followed by dissociation of the tetrahedral intermediate, where our carbon is changing from sp3 back to sp2 hybridization. In a previous slide, we talked about the relative stability of the carbonyl carbon in the different carboxylic acid derivatives to think about the relative reactivity. And we know that nucleophilic acyl substitution reactions will work in one direction, not in the other direction. Thinking about the dissociation of the tetrahedral intermediate is another good way to think about which nucleophilic acyl substitution reactions will work and which ones won't. So for example, if we want to consider whether an acid chloride can be converted to an amine, or whether an amine can be converted to an acid chloride, let's think about if this Y group is a chlorine and this other group has a nitrogen, then as these electrons come back in, it's really about a competition between whether this group is going to leave or whether this group is going to leave. So we are comparing then the different leaving group abilities. And so Cl- is going to be the best leaving group. Therefore, if this intermediate is formed, chlorine is always going to be lost, resulting in the formation of an amide, rather than the amine being lost, resulting in the formation of an acid chloride. This is something that we'll come back to as we work through the details of the mechanisms, but I just wanted to point that out here. As we consider the tetrahedral intermediate, what's actually going to exist? We might have a species that has a positive charge. We might have something where everything is neutral, or we might have something where we have a negative charge. And quite possibly, we will have a combination. Now, most likely, we would have a combination of these two if the reaction is carried out under acidic conditions, and we might have a combination of these two if the reaction is carried out under basic conditions. Now, as we compare the different mechanisms of the different reactions, we will see some different details, especially in terms of the order of proton transfer, the positive and negative charges of the various intermediates. But there are a lot of similarities. So try to focus on what's similar about these different reactions rather than getting lost in the details.